function f is said to be analytic near x equals c, some point in f's domain, if it is equal to its Taylor series on some open set that contains c, the center. We usually call c the center of the Taylor series, and we call this the coefficient for each term in our Taylor series. And of course the n works like a degree of a polynomial, so we'll call this the degree. So functions are analytic if they're equal to their Taylor series. Initially, you'd say, well, okay, polynomials are equal to their Taylor series. Most of the coefficients are 0. The functions like sine and cosine and exponential functions and tangents and things like that, I will show you in just a little bit, but they too are analytic. And so you might get the impression that nearly everything that is a function is analytic. But this is actually not true. There are a whole collection of functions that are not analytic. They're not equal to their Taylor series. Even though you can write down a Taylor series for them, they don't actually equal the Taylor series. Now, these are functions that are not largely appearing in the traditional story of calculus, but this is a somewhat non-traditional video. Because what one would do at this point is you'd start computing some Taylor series, probably have some textbook examples. Now, I encourage you to go find a textbook and play with some textbook examples. And I will compute some of them in just a moment, but I want to go a little different direction near the end. Okay, so given this kind of formula, it's probably pretty straightforward to say, well, if I have a function and I can compute the derivative pretty easily, like all those n derivatives of f appearing in the coefficient, I should be able to write down the Taylor series. That's what you'd think, and you'd be right. So for instance, a function that's really easy to take derivatives of is e to the x. So let's figure out what its Taylor series is. So the Taylor series for e to the x, well, let's say that's f of x, just to keep our notation straight. And let's find the Taylor series centered at x equals 0. So if I do that, well, I need f of 0. That's 1. I need f prime of 0. Well, what is that? That's the derivative of e to the x evaluated at x equals 0. That vertical bar, like when you're evaluating an integral, means evaluate at, but when I only have this lower marking, means just evaluate there. Don't do any subtracting or things like that. Okay? Well, the derivative of e to the x is e to the x, and so I'm going to evaluate it at x equals 0. That's e to the 0, which is, of course, 1. And, of course, the pattern is all of these other derivatives, all of them, they're equal to 1 as well. So putting that right into the Taylor series formula, I'm telling you that e to the x is analytic. This requires some proof, but I'm telling you that that is the case. Just pop it right into the formula, and all the derivatives are 1, and the center is 0. Put it another way, it looks a bit like this. 2 factorial is just 2, 3 factorial is 6, 4 factorial is 24, and so on. So this is the power series, the Taylor series, for e to the x. Just as a side note, sometimes people want to use a fancier term when a simpler one will do. Taylor series centered at 0, sometimes people will call it a Maclaurin series. Don't let that bother you. It's just a Taylor series centered at 0. Now, great. That's the series for e to the x. Does this actually converge? Well, does it converge to e to the x? How does it converge? Well, this is best done by plotting. So, here's the degree 0 in red term, and in black is e to the x. And you'll see, yeah, they agree at 0. It's kind of close, if you're close, maybe. I don't know. It's not a very good approximation. But if I add another term, now this is a linear approximation. This is the tangent line at x equals 0. And you see it does a better job. Of course, derivative, tangent line, degree 1, Taylor series. all kind of fit together. All right, well, if I start adding more terms, hey, there's a degree 2 Taylor series, and it does a pretty much better job. You can see that actually pretty close to x equals 0, you really can't tell which curve is which because they overlap so well. But as you start to get around plus or minus a half, you start to see some difference between the Taylor series and the actual function. Adding another term, and you can see that it really fits very nicely now. In fact, this is how we compute e to the x in the computer, is with a Taylor series. Okay, well, if that was so easy, what about another function? Let us try cosine of x. So, g of x is equal to cosine of x. All right, let's start taking derivatives. G prime, G double prime, G triple prime, and G4 prime, i.e., yeah, just 4 derivatives. Okay. So, if I take a derivative of cosine, I think you'll agree it's minus sine. Take a derivative of sine, it's cosine, but there's still a minus sign left over. And one more derivative, so take a derivative of minus cosine, I get back to plus sine. And take a derivative of sine, I get back to cosine. And at this point, we're back to where we started, and the pattern repeats. Okay? So let's evaluate these at 0. We'll find the Maclaurin series, or the Taylor series, centered at 0 for cosine of x. Okay, well, cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1, so that's a negative 1. Sine of 0, still 0. And cosine of 0 is back to 1. So this means, again, I'm telling you that cosine is analytic. That requires proof. But since it is, this is what it looks like. So that there's a 0 term here for the x. Then I get a minus x squared over 2. My coefficient out front is a 1/2, minus 1/2. And then there's a 0, x cubed, and there's a plus x to the 4th over 24, and so on. Usually when people write the series for cosine, they just leave out the 0 terms. And since this series does actually converge, this is a power series, you can check its radius of convergence. So, homework, check radius of convergence. It is infinity. So, go ahead and try that yourself. It's not so hard. Hint, use the ratio test. Okay, but that said, let's see what this does. Okay, so just as before, we've got the cosine curve in black, and we've got the Taylor series in red. This is the degree 0 Taylor series. The degree 1 Taylor series isn't very different, because it's just add 0. But the degree 2 Taylor series, hey, that's a pretty good match kind of near the origin right away. So what this says is, it says if you're close to x equals 0, cosine pretty much looks like a parabola. All right, moving right along, adding 2 more degrees because the degree 3 term is 0. No, not a bad match at all. Starting to really fit the shape of the cosine. And actually what you could do, even with this degree 4 approximation, if you wanted, you could make use of the fact that cosine is periodic and cut it off at pi over 2. That's like 1.5 and change. So right where this red curve crosses the x-axis. And just keep reusing the center segment over and over. And you'd get a pretty good approximation of cosine. That's what this graph is showing you. And in fact, some old computers, that is what they did. But, we could do a little bit better. We could add another term. and another term. You can see that we start to come and loop around and slowly wind over each of the twists and turns of the cosine. Okay, so that was pretty good. And what about sine? What about sine? Well, same kind of pattern. Let's find out what h prime of x is equal to. H double prime, h triple prime, and 4 primes. As you might imagine, it's going to repeat just like the cosine did, for essentially the same reason. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of minus sine is minus cosine. And one more derivative, we come back to where we started. And the process repeats. Again, let's evaluate each of these at 0. Okay. Sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1, but I've got a minus sign already there. And back to 0. So, again, because sine is analytic, again, I'm telling you that. It requires proof. The first term is 0. I'll leave it off. The second term is x. The third term is 0. The fourth term is minus x cubed over 3 factorial, which is 6. And then plus. And I think the pattern is pretty clear. You can pick up all of the odd degree terms. 5 factorial is 120. And then the next term is minus, and so on. Okay, again, let's see how this looks graphically. So, once again, in black is sine, in red is its Taylor series. There's the degree 0 Taylor series, just constant at 0. Doesn't do a very good job at all. Here's the first degree 1 Taylor series. It's a tangent line, and you can see, yeah, it's pretty close to the origin. Sine of x looks pretty much like x. Okay, that's a good motivation to use radians, by the way. All right, let's add another non-trivial term, non-zero term. That next one is x cubed. And hey, this is doing a pretty good job near the origin, for sure. You can't even tell the difference between these two curves. Adding another term, hey, now we get around the hump. Like the cosine, if you go from minus pi to pi, you could just repeat this function over and over to trace out a pretty darn good approximation of sine. Again, computers sometimes do this. This is a pretty fast way to estimate what sine is. And of course, adding one more term, we've got now an x to the 7th, and we basically get a full period of sine. Not bad at all. Okay, now, given these things, I want to show you a few things about these 3 series that we just wrote down. They are e to the x, cosine of x, and sine of x. Now, if you look at these, you can say, hey, these are all pretty closely related. You'll notice it almost looks like if I take the cosine terms and I add the sine terms, I'll get e to the x. That's almost true, except that the signs are wrong. The SIGNs, not the SINEs. What Euler, Leonhard Euler, the mathematician who is known now to history as analysis incarnate, noticed. He noticed this and he said, hey, I bet I can fix up those signs, but I'd have to leave the real world in order to do that. I need to make use of the imaginary world. Now, what is that? Well, the imaginary numbers are those that look like I, which is the square root of -1. Now, if you remember your algebra, you probably are told never take the square root of a negative number. But what if you do? Well, it has the property that I squared is equal to -1, and I cubed is equal to minus I, and I to the 4th is equal to back to 1. Huh. And if you do this, contrary to the cautions of your algebra teacher, nothing bad happens. In fact, quite the opposite. Many good things happen. This is actually a phenomenally good idea, is to play with numbers that involve the square root of -1 and to allow them into existence. If you do that in the right way, you can actually line up sine and cosine to get something with e to the x. How does that work? Well, let me show you. This is one of those amazing little things that Euler has taught us. So what Euler said is, you know what, let me, instead of evaluating the Taylor series for e to the x, let me look at e to the ix. The first term is just 1, and it's ix. The next one is I squared, x squared over 2. I squared, though, is -1. So let me write that out. The next one is negative I times x cubed over 6, because I cubed is negative I. I to the 4th is 1, okay, so that's unchanged. What about I to the 5th? Well, the pattern restarts. So he said, let's try that. Now notice the signs, SIGNs, match the signs for the sine and cosine. Let me get this out of the way, and you can maybe see that. So for instance, the signs on e to the ix go plus, plus, minus, minus, plus, plus, and of course then they go minus, minus. You will notice the signs then match up with the signs that you need. The first plus matches up with the plus of the cosine. The second matches up with the plus here. The third matches up with this minus. The fourth matches up with this. And then plus, plus. So the signs actually matched up. Now, the only problem here is that we've got an extra I floating around occasionally. This one here, and this one here. You will notice they only show up on the sine terms. So if I go through it, say, I times sine of x, I'd get an ix, and a minus ix cubed, and a plus ix to the 5th. Now they actually match up exactly. So in particular, what this has found us is this amazing identity that is now attributed to Euler. People usually call it Euler's identity. Is they say if I add up these two expressions, you have cosine of x plus I times sine of x is equal to e to the ix. Now, that looks like a whole lot of black magic, but it turns out to be really, really valuable. In particular, this means that if you know something about sines and cosines, it's really something about exponentials. Kind of amazing. Now, sometimes it's handy to have an explicit formula for sine and cosine. If you go ahead and solve this expression for sine and cosine, you'll end up with a little bit of algebra. I won't have you show you the details, but there's a little bit of algebra, in particular a little bit of complex number algebra. We find actually that there are two formulas, one for cosine and one for sine. And these two formulas can make short work of all the trig identities you can imagine. All the trig identities come out of this, including the Pythagorean identity, the double angle formulas, the half angle formulas, and pretty much any other trig identity you can imagine. They all spring from these two formulas. So if they seem a bit mysterious, well, they are. They take a bit getting used to. But these are the sorts of things that you can get analytically from the power of Taylor series.
So now you know the Taylor series for sine, cosine, and the exponential function e to the x. These are pretty useful for doing calculations by hand analytically, but they're actually also useful for automatic computations as well. See, nearly every computer, be it a laptop, a mini computer from the 1970s, or my trusty graphing calculator that I've had with me since I took calculus, all of these devices can only add, subtract, divide, or multiply in hardware. And some of them can't even divide or multiply. They can just add and subtract. But with Taylor series, you can combine these four operations to approximate the values of any non-elementary function, like a sine or a cosine. So that's actually how these devices compute sines and cosines and exponential functions, logarithms, Bessel functions, and many more, is by way of their Taylor series.